So now we will discuss that how to estimate these probabilities that what we have discussed earlier. Uh, so in yeah. So these how we are going to discuss this probability or this probability or these probabilities. So that is what we are going to discuss now. So before that, we have to understand that we will get our three types of the data. So one is the training data, and we will use training data to estimate those probabilities. Development data, or this comes with the other name like validation. So validation data is to sort of understand that how good is my estimates, or let's say that how good is my trained model is. And the test is that that you should never use unless you are certain that now this is the final model which you are going to be keeping. So the test data is completely independent data. It should never be used while you are still judging that which model or which model you should use for your data. So for example, in this case the language model, we have these different options that whether we use this unigram probability estimates, or whether we use the bigram, or whether you use trigram, or we should increase this n-gram model. So and how does this impacts the performance, all of these things. So estimation of all those required probabilities should be done using the training data, and judging that or comparing that which of these is, for example, unigram or bigram or trigram, which among these model is the most suitable or has given us the best performance. That has to be sort of first checked on the development or the validation set. And once you are decided that okay, now this is what your model should be, and then only you should use that on a test set. So the estimation is done using our old friend, the maximum likelihood. I hope all of you have by now understand the maximum likelihood. And if not, I will ask you to sort of first understand that what is the likelihood function means, and then only you should try to sort of understand that what is the maximum likelihood estimation. So if you have already gone through the collocation chapter and understood how the while calculating this t-test, how those probabilities were estimated, how let's say that these bigrams or the unigrams were converted into indicator random variable, and those indicator random variables were considered as a Bernoulli distribution, and then how that has been considered as a if you go pass through your corpus, that corpus seeing your unigram or bigram, whatever you are looking at it. So for example, if you are looking at the bigram, so corresponding to that bigram, whenever you see that particular bigram, your indicator random variable gets the value 1, and if you don't see the bigram, then it gets value 0. And each of these observation is assumed to be independent, so sort of equivalent to kind of tossing a coin n times, and each of the coin toss is sort of independent of the previous toss of the coin, and you are doing n number of such coins. So here n would be that the n times you are going through your corpus, and if you are considering the bigrams, you are looking at the n bigrams, and whenever you see that the target bigram is present, then it gets the value 1. If it's not, then it is value gets 0. And so now seeing that that particular bigram, that is a probability P, and that how you are going to estimate, and and that you can estimate using the maximum likelihood estimation. And that maximum likelihood estimation is basically, in case of the unigram, gives this formula. In case of the bigram, gives this formula. In case of this n-gram, which is just a generalized form of it, gives us this formula. So I hope each one of you are able to do that. If you not, then again I am sort of repeating this, that first what you should do is that you consider that if you have a so I'm sort of rephrasing the exact problem, forgetting about anything related to the bigram or natural language processing. I'm completely converting into a statistics problem, that you have a random variable x, which is the Bernoulli distribution, and or having the coming from the Bernoulli distribution, and Bernoulli distribution has just one parameter p, which is corresponding to, let's say, the probability of success, or probability of success, or probability of, if you are relating with the coin toss, and if head is corresponding to your success, then you can say that this is a probability of seeing a head. And if you are making, let's say, that n observations, so your experiment you have done is the n observations for this particular random variable. So you might have the two possible value, whether x will take the value 1 or it will take the value 0. So if having these informations that there are n observations, then in that case, and each of these of course it is a Bernoulli distribution, so these n trials, or you can let me also write it as an n trials. So this is sort of the independent of each other. Having that information available to you, how you are going to estimate this probability using the maximum likelihood estimate. So this is the kind of a homework. Do it yourself, and if you have already gone through the the collocation chapter, I think that has already described these things, and some of the steps might be missing, but then if you are able to solve this part, then I think you will be able to understand everything here. So you can say up to now whatever we have discussed, so the only mathematical background or mathematical formulation we would have required is understanding of the likelihood function, understanding of the maximum likelihood estimation, and how you are going to estimate for a Bernoulli distribution. How you are going to estimate the probability P for Bernoulli distribution using the maximum likelihood estimate. So if you know this much, so up to whatever we have discussed, as per the mathematical background requirement is there, it's done. If some of you have a problem, please do let me know. But since this is a very, very fundamental thing, if you just search on the net, if you are not able to do it yourself, you should find a solution. But still, if some of you have a doubt or confusion, please do write to me. So now, given that we do this maximum likelihood estimate, and depending on model we can choose which, if it is a bigram or trigram or and so on, we have these probability estimates available to us. So here the C is basically just the count. So this is an example. I have taken it from the Joravsky book, and it says, I think this is this, I'm not sure whether it's from the third edition or the second edition, I forgot. But anyway, so the idea here is that these are the bigrams in a particular corpus they have, and this is the bigram probabilities, just shows this is a table. And if you want to compute the probabilities that I want to eat British food, then since this is a bigram, so you have one spatial symbol here, and of course you remember that this corresponds to the our stop symbol. And if instead, so this is a this probability is written, of course this is an approximation, and under the bigram estimation, or you can say that first order Markov assumption. This is what this probability is kind of an approximated using this right hand side. Okay. But if it is a trigram model, then instead of having so the first term would be written as the probability of I, given, let's say that either you write star, this special symbol, or you can say star star, it's the same. So basically you are sort of padding your sentence with some special symbol, and then you have this probability of want given I, the given star and then I, and then you will have probability of 2 given erasure, no, yes, erasure, no, so sorry for that. Okay, so what I wanted to write here is that I, okay, now it's working, I, and then want. Okay, now this ink color has been changed. Let me see if I come back to this pen. Okay, fine, now this would be I want. Okay, so now there's some ink having some issues, but anyway, so that's what, so this is a bigram estimation that if we are going to do, and this is under the trigram model, and then and so on. So you continue try to write like that. So that is the way you are going to estimate probability of any given sentence under these various models. So now let's look into that, how we are going to evaluate these models. So there are two different ways. The first one is the intrinsic evaluation, and second one is the extrinsic evaluation. So intrinsic evaluation is that you don't, given your own data set, you want to look into you define a metric which is given only on that data sets, and then how you have defined a particular model, you try to evaluate implicitly there. But in case of the extrinsic evaluation, what we do is that we look into some third task or some different task, and then we want to sort of evaluate that one. So that is why it's called the extrinsic evaluation. So the perplexity is the common way to evaluate any language model. So if we have a test data of m sentences, so let's say that S1 to S1 to SM, these are the m sentences in your test data, and for each of these sentences you have this probability based on whatever you have estimated using your training data, and then you take the log probability of all sentences. So basically the perplexity is defined as the joint probability distribution of each of you can sort of consider for all of them, all sentences, probability of this one, and you assume that each sentence are the independent, so you can write that as a product of each probability of each of the sentence. And then considering this, what you do is that you take the log. So taking the log has a usual advantage. Again, this is for you to think that why we should take a log, what kind of advantage it gives, and then this would be now the summation of log p of si. So that's what we have. So there's a sort of in literature often we have the different definitions, or the most common way to express the perplexity is in terms of the 2 to the power minus L, where L is nothing but it takes the average over this the joint probability which you have considered, the log probability, and this capital M is basically counts the number of tokens, total tokens present in all of these sentences together. So if I write that the Ni is the number of tokens in the sentence Si, then I am going to sort of sum all of them together, and that is what the capital M is. And so this is the number of tokens in sentence Si. So then so these are the different ways to define perplexity. So this is the first one, is the most common way to define perplexity, and the smaller the value of this, the better the language model is. Often we interpret perplexity as a weighted average branching factor, meaning thereby is that branching factor implies here that what is the number of possible next words that can follow any word. So for example, let's consider that your vocabulary size is, let's say, that 10,000. So for any given word, now you can assume that there are approximately 10,000 possible words. But if I have understood my the language, and if you are writing the correct sentences, then it should dramatically reduce the number of possible words. So that's what in some way this perplexity is trying to sort of estimate, that what could be the possible correct next word which can be there. So that's what we interpret, and it has sort of several based on the information theory, there are a few other interpretation, but this is the one which I find it very convenient to understand in the context of the language model. Now let's look into some of the specific examples that if you have about this example sort of, if I try to compare the perplexity of the different language models, so here the probabilities were estimated on a corpus coming from this Wall Street journals. The total number of words or the tokens were the 38 millions, with the vocabulary size of about 20,000, and the test has about 1.5 million tokens. And when you train with the unigram model, the perplexity was 962, the bigram has 170, and the trigram has 109. So you can see that, and remember that the smaller the value, the better is the language model. So the trigram model is definitely in this particular case seems that gives the better performance. And that is also comes along with our intuition, because you know, unigram you are not considering any context, bigram you are considering only one context word, only the last word, and the trigram you are considering the last two words. So it actually improves that what could be the next word. So that those based on that intuition also we can see that the trigram model should perform better, and that is what actually empirically also we observe in this particular example. Now you know, in the generalization we want to see that how this if you train on a particular corpus, then what kind of a word these different this language models you know generate. And since this model was trained on the Shakespeare work, so when he tries to generate the sentences based on the unigram model, you see that it does not make much sense. But when you have this the bigram, then it does somewhat is making better sense. The trigram has in fact even it's better, and the foregram, you know, you can see that it actually reflects quite well, and it is somehow it looks like that yes, this could be a correct sentence, and this could be a you know so this you know in a way it shows that you know, you increase the context size, the probability estimate should be better. And if you're using those probability estimates, if you try to generate these sentences, it will lead to the more natural sentences would be able to generate. So, and you can also see that so there is another model, but then this time this is generated using the Wall Street Journal, and you can see that the kind of sentences or the words which are appearing based in each of these cases is some completely different. So that is why again it is very important that whenever you train a language model, you have to make sure that, and if you want to use it for your own purpose, you make sure that if you're using any pre-trained language model, so those pre-trained models should be trained on a similar kind of a text data than that which you want to use it for yourself. So for example, the Shakespeare words, so you can see that the words which are appearing here, they are completely different than the words which are appearing in case of the model which was trained on the Wall Street Journal articles. So this again highlights this importance that the genre has its relevance, and you have to be very, very careful that where is your these language model has been trained on what kind of a text, whether you can directly use it or you have to fine tune further based on whatever is your requirement or the data on which you want to use it. One of the things which we have to sort of careful about is that, you know, even if we are estimating these probabilities, some of the counts can still be zero here. So we will again discuss in the next lecture, we will discuss that what kind of an issues or still the n-gram models have. But one of the easy one to handle is that unknown or the out of vocabulary words. So there are two ways. The one is that if you have the very fixed vocabulary, and what you can do is that the words which are not appearing in words which are outside of these vocabularies, you can consider or put them into an unknown category, and then and then treat that unknown as any regular word. So all of the words which are not present in your fixed vocabulary are mapped to a unknown category, and this, for this particular category itself, you count, whenever those words are there, you will count, and then you will increase the count of unknown words, and then you uh, uh, estimate or all the counts or the estimates corresponding to those words will relate to this unknown word. But if you don't have a fixed vocabulary and you are creating your own data or the corpus, what you can do is that you can first look into the frequencies of all the words, and then the words which has you can choose a threshold that if the words which are appearing less than 5 times or 10 times, you will put them into unknown category, and rest others can be they are whatever the words they are. And yeah, and then so that in that way your vocabulary is that all the words in its usual form and appearing more than, let's say, that 5 times, you will always you will put them into directly into your vocabulary, and all the words which are coming which are occurring less than 5 times has been put into a unknown category and be considered as the same. Okay. So now in the next lecture we are going to discuss that what kind of issues are there with this n-gram model, the estimation of those probabilities, and how we are going to deal with them. So this is again the n-gram model still has this kind of an sparsity issues, that if something which we have observed in the training sets, but then some kind of sentences or some kind of a phrases which we have not seen in my training set, again this n-gram model will also underestimate those probabilities, and then how we can take care of such cases is we are going to discuss in the next class. So okay, thank you, and I hope that you watch this video and you will get the understanding of that how do we define the language model, what is n-gram language model, and how do we evaluate language models. Fine, thank you.